It turns out that this question is a demonstration of Newton's law of cooling. We have written that law right here. It's a differential equation. It basically just tells us that how fast an object is cooling is going to be proportional to the difference in temperature between the object and the ambient temperature. So the greater the difference between an object and the surroundings, the faster the object will cool, and the lower the difference between the object and the surroundings, the slower that object will cool. Now, we have to take some of the data and write it down in sort of a mathematical form. So we know that the thermometer begins at a temperature of 70 degrees. So we can say that T of times 0 is equal to 70. And it's moved into the outside where the ambient temperature is 10 degrees. So T sub m will equal 10. And then after 1/2 of a minute, the thermometer's temperature is 50 degrees. So we could say that T of 1/2 is equal to 50. And then our objective in this question, or the first objective, is to figure out what the thermometer's temperature is after 1 minute. So we need T of 1. And in order for us to do that, we have to solve that differential equation. So let's go ahead and rewrite it. There we go. Notice we have plugged the 10 in for the ambient temperature, T sub m. Now to solve this, we're going to separate variables. And perhaps the first thing to do in that objective would be to multiply both sides by dt. So that would cancel it out on the left side. Next, we will divide both sides of the equation by this term t minus 10. That will cancel it on the right-hand side. And we have done it. We have separated the variables. Notice that the temperature variable is gathered on the left side and the time variable is gathered on the right side. So that's a successful separation of variables. Next, we would have to integrate both sides of this equation. So we will do so now. The left integral is somewhat sticky. If you know how to do it, you can skip ahead a minute or two to the next part. But for those who want a quick review, you would have to do a u substitution. So you would let u equal the term in the denominator, the capital T minus 10. You would differentiate both sides with respect to temperature. So in other words, du dt. The derivative of 1t is just 1, and the constant 10 goes to 0 when you differentiate it. Multiply both sides of that by dt, and you can see that du is equal to dt. Now you go back and make a couple of substitutions here. This dt, as we just showed, is equal to du. And then the denominator t minus 10, well, that was equal to the u. So you have the integral of du over u. From calculus, we know that this is equal to the natural log of the absolute value of u. And if we replace the u back with the t minus 10, we have the natural log of t minus 10. So that was an overview of how to integrate the left-hand side. Returning to the main problem here, we have the natural log of the absolute value of t minus 10, and then this was equal to the integral of k dt. Now that integral is a little less intimidating. You can factor out the constant of proportionality, and then you're just integrating dt, and of course the integral of dt is just t. So the right-hand side becomes k multiplied by t plus an arbitrary constant of integration. We are getting there, but to solve for the capital T, we would have to raise e to both sides of this equation. What that does is it cancels out the natural log. Remember that the natural log and the base e exponential function are inverses, so they cancel each other out. This leaves us with t minus 10 is equal to e to the power of kt plus c. We want to rewrite the right-hand side. To do that, remember that one of the laws of exponents allows us to take an exponential that is raised to the power of a sum and rewrite that as e to the power of a times e to the power of b. And so to rewrite the right side, following that rule, we would have e to the power of kt times e to the power of c. Very good. Now, it turns out it will be helpful if we could figure out what the heck this is equal to, e to the power of c. And to do that, let us recall that the initial temperature of the thermometer was 70. So what we're going to do is we're going to plug 0 in for little t and 70 in for capital T. So if we do that, the left side becomes 70 minus 10, which is just 60. E to the power of 0 times e to the power of c. Recall that e to the power of 0 is just 1. So voila, we can see that e to the power of c is equal to 60, which means that we can rewrite this equation as t minus 10 equals e to the kt times 60. And in fact, the right side would look a little nicer if we reversed it. So here we have t minus 10 equals 60 times e to the kt. And that is looking pretty sharp. Now, we're still not done because we have to figure out what the value of k is. Let us recall the question tells us that the temperature after half of a minute was equal to something. I kind of forgot what it was. Maybe it was 50. It was. So we're going to go ahead and we are going to plug in 1/2 for little t and 50 in for capital T. So on the left side, you'll have 50 minus 10, which is 40. On the right side, we're going to plug in 1/2 for little t, so you're going to have e to the 1/2 times k. We would divide both sides by 60. So it would look like this. Divide this side by 60 and this side by 60. Looks like the left side is going to become 2/3. We have e to the 1/2 times k. We're going to solve for k by taking the natural log of both sides. So you take the natural log here and there. Again, natural log and e cancel each other out. So you have ln of 2/3 is equal to 1/2 k. And then you would multiply both sides of this equation by 2. You'd have 2 ln of 2/3, and then on the right side you'd have 2 times 1/2 k. The 2 and the 1/2 cancel, so you basically just have k on the right side. So that is the value of k. You could pick up a calculator and estimate it. It's roughly negative 0.8109 is the approximate value of k. So far, so good. We can now actually prepare to answer the main question. Let us go back and grab this solution to the differential equation under the given conditions. The question wants us to figure out the temperature after 1 minute. So we need to figure out T of 1. So we will simply plug in 1 for T. Recall, by the way, that this capital T is the same thing as T as a function of time. So if you prefer to write it that way, that is perfectly reasonable. Let us also plug in the value of K. And now we plug in 1 for little t. And we're going to end up solving for this T of 1. Maybe pick up a calculator and type in the stuff that's on the right-hand side. You're going to get about 26.6 repeating. And then finally, you can add to both sides the 10. And look at this. The temperature after 1 minute would equal 36.67 degrees. I believe this was in Fahrenheit. So that would be the correct answer for the first part of the question. There was another part, though. So we just go back, check it out. Way up here, it said... How long will it take the thermometer to reach 15 degrees Fahrenheit? Okay, so let's go back and find our trusty equation. It's right there. Let's copy and paste it. Okay, and so we want the temperature to reach 15 degrees. So what you're going to do is you're going to plug in right there the 15 degrees for the temperature. And now your objective becomes to solve for the time, the lowercase t value. Not too bad. Subtract on the left side. That's going to give you 5. And then you're going to want to divide both sides of this by 60. So let's just do a little copy and pasting, or perhaps we should not have done that. We won't do that because that seems to have backfired. So we will just divide both sides of this by 60. Looks like you're going to get 1/12 on this side. And then finally, let us take the natural log of both sides. When you take the natural log on the right side, it's going to cancel out the e. So now you have the natural log of 1/12 is equal to this negative 0.8109t. Divide both sides by that negative 0.810t, and you will get your answer. And when you do that, you will get about 3.06 minutes. And that would be the correct answer for the second part of that question.